All right, everyone, I wanted to put together a quick video to help out on some of the trickier parts of this lab experiment, the kinetics of the iodine clock reaction. Um, so in this particular experiment, we're looking at what is the kinetics of this reaction. So these three chemicals reacting to give us those three products. And I think where the confusion was doing some of the calculations in here. So the first place that I saw that there were a few issues was figuring out the concentrations for the rate law. And I want to point out, so often we'll call what's given up here as the bottle concentration. So if you were actually in the lab, these would be the concentrations that are on the bottles. But we need to figure out what the concentration of those reagents are in our reaction. So one thing that's nice about how this table is set up is that all of these total, if I total all the way across here, 300 plus 600 plus 300 plus 150 plus 150 plus 300, for each one of these, and I verified this, for each one of these it totals to exactly 1800 microliters. Okay, so there's, since it works out that way, there's a really easy way for us to go through and quickly figure out what these concentrations will be in the solution. And what I'm going to show you, it's the same process as using the dilution equation. The M1 is essentially the same as this. M1 times V1 equals M2 times V2 that you might remember from first semester of general chemistry. But it's just another way to think about it and probably a faster way to look at it. Okay, so if I want to know ultimately for this experiment A1, what's the concentration of potassium iodide that's in there, I'm going to go and take my concentration. My bottle concentration is 0.0100, and I'm going to multiply that by 300 over 1800. 300 divided by 1800. And let's go ahead and put all these in scientific notation. 1.67 times 10 to the minus 3. Here's another one. Okay, bottle concentration is different though. So our bottle concentration here is 0.1 rather than 0.01. So let's put that one in the calculator too. 0.100 times 300 divided by 1800. 1.67 times 10 to the minus 2. Okay, it's minus 2 because this acid is more concentrated than the Ki solution was by a factor of 10. All right, this one, 0.00100 times 150 divided by 1800. 8.33 times 10 to the minus 5. And then finally this bromate reagent that we have here. 0.0400 times 300 divided by 1800. 6.67 times 10 to the minus 3. So those are the molarities of everything for the A1 experiment. So what's nice about this, and you can knock this out really quickly, is that, well, for one example, so all of these have 300 microliters of the Ki out of a total of 1800 microliters for the solution. So all of those are 1.67 times 10 to the minus 3, 1.67 times 10 to the minus 3, 1.67 times 10 to the minus 3, 1.67 times 10 to the minus 3. So all in that column that are 300 microliters are that same concentration. This is double the amount. So if I just take my 1.67 times 10 to the minus 3 and double it, .33 times 10 to the minus 3. Or triple it, 5.01 times 10 to the minus 3. Okay, so you want to go through And if you can print this out, this is the easiest, is just to go through and fill out the chart here and then transfer all that data to table number, table A. So, table, okay, page 7, table number B, table letter B. Okay, and so you could go and just transfer all of that data over there. So I did, for me, I thought it was easier to write it out and then rewrite it over here. Transferred it from there to my table that's here. I worked all those out. And those would be the same for you, so if you want to stop the video there and copy those, you can do that too. All right, this is probably where the main confusion came, is from working through to figure out the initial rate of the reaction. And what I'll draw your attention to first here is the fact that, so this guy, this S2O3, 2-, is not involved in the reaction. This is actually acting as an indicator for us for I2. This reacts with I2. And so at the beginning, this is in there, and then it very rapidly goes away as I2 is formed. And so what that allows us to do is figure out how rapid, just by looking at it, how quickly I2 is formed and is chewing this up. And so mathematically, what do we end up having to do here? So to get our initial rate, we take this, because this goes all the way down to 0. It starts as 8.33 times 10 to the minus 5. It goes to 0. And it takes that long to do it. Okay, so it went, so the concentration change went from 8.33 times 10 to the minus 5 down to 0. So 8.33 times 10 to the minus 5 minus 0 is 8.33 times 10 to the minus 5. And it happened over this length of time. So basically, mathematically, I take this number, divide it by this number, and I'm given my initial rate here in molarities per second. All right, what you're going to do after that is you're going to take and that data from table C, and then you're going to do some calculations here. And for the first ones, it tells you what to do. So for the first ones, it tells you to take A2 and divide by A1, and to take the rate ratio and the concentration ratio, and then to take the natural log of both of those and then figure that out. Let me show you why you do that now. All right, my camera crashed there, so if there's a little bit of an odd transition, that's why. The ones from the videos that I had showed you guys, and the way that I usually talk about this, is I picked examples where we have something like 3 to the x equals 9, okay, where it's very obvious that x is equal to 2, and things like that. 4 to the x equals 4, okay, x is equal to 1, or 11 to the x equals 1, and then x is equal to 0. So ones that we can kind of see by inspection. What the lab report is having you guys do, since you're working with experimental data, it's better to do this, is to use the logs to actually solve for the value of x. And what we can do is, when we have a problem such as, so you would end up with scenarios where you had something maybe like, okay, so you could end up with a scenario like that. And for me anyway, if I look at that, it's not obvious what the value of x should be. And so there's this nice property of logs where if we take the log of both sides, natural log of 1.7 raised to the x power is equal to natural log of 2.89. Well, this nice property that the logs have is this x can come out of the parentheses, and it becomes x times natural log of 1.17. Okay, now the calculator can do a lot of the work here for us. So then x is equal to natural log of 2.89 over natural log of 1.7. So for the top, natural log 2.87, 1.05, and then the bottom, natural log 1.7, 0.530, 1.05 divided by 0.530, 1.98, so essentially 2. Okay, and experimental data doesn't come out to be exact most of the time, the way the simple examples will show, and so you would need to do something like this in order to solve for x. Okay, this is not something that I would ask you guys to do on a quiz or an exam, but this is something that they've asked you to do in this problem. All right, the final thing I want to show you, and I'm pretty sure everybody can handle this part, I was just going to go ahead and put it in the video anyway, is it asks you to calculate the value of k based on each experiment. And rate is equal to, a little bit of a spoiler here, I'm going to tell you the rate law in order to show this to you. Okay, I to the first power, BrO3 minus to the first power, and then H plus, the acid, squared. So now, for example, from trial 1, my rate was equal to 8.53 times 10 to the minus 7 molarity per second. My concentration of I from that first one was equal to 1.67 times 10, just pulling this from my table, 10 to the minus 3 molar. BrO3 minus concentration is 6.67 times 10 to the minus 3 molar. And my concentration of H plus is 1.67 times 10 to the minus 2 molar. Well, now I just got to rearrange that and solve for K. K is equal to rate divided by everything else. I minus, BrO3 minus, and H plus squared. Just got to put my numbers in there now. 8.53 times 10 to the minus 7 molarity per second. 1.67 times 10 to the minus 3 molarity. 6.67 times 10 to the minus 3 molarity. And 1.67 times 10 to the minus 2 molarity. And that whole thing, including the unit, gets squared. When I put this into my calculator, I get a number 275 out for the rate constant. And then it also asks us to do the units. So let's just do math with the units. Meters per second on the top, molarity per second on the top, molarity times molarity squared. Just like regular algebra, m cancels m, and so we're left with molarity to the minus 3, s to the minus 1. 275, m to the minus 3, s to the minus 1.